Previously, we've seen how we can use the pigeonhole principle for proving claims, including those in graph theory. I thought I would show you an example of using the averaging principle to prove a graph theoretic claim. Now, as a reminder, the averaging principle is simply that if I take a collection of n numbers, the averaging principle states that there exists a number that is at least the average of the collection, and there exists an element that is at most the average in the collection. So we're going to prove a really basic property of graphs. So for any undirected graph. Oh, I don't like this marker. Let's switch to another one. I got a bunch of markers here. The question is which one? Which one? For any undirected graph, G is equal to VE with n vertices. With n vertices and m edges. If the number of edges is strictly less than n-1, then the graph G is disconnected. So that's a fun remark. If you have, say, exactly n-1 edges and your graph is connected, it's a tree. So we're going to give characterization when we have too few edges to end up with a graph that forms, say, something like a tree or a forest, or more. So we're going to do this by proving this claim using mathematical induction. So let us perform induction on n, the number of vertices. So we're going to denote a statement. So we're going to let d of n denote the statement the following statement. For any graph G on n vertices, if the number of edges is less than n-1, then G is disconnected. So just as a reminder, disconnected simply means that there exists at least two vertices such that there does not exist a path or a sequence of adjacent vertices to reach that other vertex. So just as a quick example, this is the disconnected graph because no vertex these vertices can't, none of them can reach that one. It's not reachable because there does not exist a sequence of adjacent vertices that I could, or path that I can walk from here to there. So, as this is an induction proof, we're going to start off with our base steps. So here I'm going to do a couple. So we're going to start with n is equal to 1. Now this is one of those weird cases where the statement becomes vacuously true because the statement doesn't even just sit, the condition can't even be applied when n is equal to 1. If n is equal to 1, the statement is what we call vacuously true. Vacuously true as the number of edges is never less than 1 minus 1, which equals 0, right? The number of edges have to be negative. That doesn't make any sense, right? So let's do another base step just to play it safe. Keep in mind, you can do as many as you like, but we just need enough to make the jump. I would like to have it so that there's at least 2 vertices, other vertices that are present in the graph. So I'm going to go up a couple steps. If n is equal to 2, then d of 2 considers graphs on 2 vertices. With less than 2 minus 1 equals 1 edges. A graph with no edges consists of isolated vertices. Those are vertices that you just can't reach. They're just sort of sitting out here. In fact, the graph that I'm talking about would look like this. Just has 2 vertices like this, no edge. No edges. Consists of isolated vertices. Hence is disconnected. Hence is disconnected. Okay, that proves d of 2. So now we got our base steps in play. Now we're going to do the induction step. Now this is where we're going to get a little bit interesting because I'm going to pull out a couple of useful tools. One is going to be the averaging principle. Another is going to actually be the handshaking lemma, which we've previously proven using double counting. So let's do the induction step. So remember, this is just saying that if d of k, then d of k plus 1 follows. So we're going to fix some k greater or equal to 2. And we're going to now assume what we're going to call our induction hypothesis or inductive hypothesis. It's going to look like this. So for any graph G on k vertices, if the number of edges is less than k minus 1, then G is connected. So that's what d of k is. We're going to assume this holds. So this is our induction hypothesis or inductive hypothesis. Now we're going to show that d of k plus 1 holds, or follows. Actually, it follows. We wish to show that d of k plus 1 follows, which is the following. So it's everything I just wrote up there, where we replace everything with k, that was k with k plus 1. So we have to be careful with this. It's very easy to accidentally be sloppy here. So for any graph on k plus 1 vertices, if the number of edges is less than, okay, so in there it's k minus 1, but remember now we're 1 higher, so now it's going to be k minus 1 plus 1, which is just k. Less than k, then G is disconnected. So we want to show that d of k follow. If d of k, then d of k plus 1 follows. So now we have the setup for the induction step. Now, we're going to use a fact so that we can express something quite nice. Namely, we're going to use the handshaking lemma to help us express the average degree of a vertex. And you're going to see how we're going to use this. This is really actually quite clever. So now that we have a graph with k plus 1 vertices, so we're going to consider any graph g is equal to VE as in d of k plus 1. We're going to presume it's satisfying. It looks like this. It's going to have k plus 1 vertices, and it has less than k edges. So by the handshaking lemma, which we've previously proven, by the handshaking lemma, we actually get a nice bound. But just as clarity, the handshaking lemma says this, that the sum of the degrees of the vertices in the graph is equal to exactly twice the number of edges. That's what our version of the handshaking lemma states. So now that we have this, let's proceed. Then the average degree of a vertex is as follows. So you would agree with me that I just simply take the sum of all the degrees of all the vertices, and you divide by how many vertices there are, right? So that's just how many vertices I have. The handshaking lemma says that this is 2 times the number of edges. I'm just going to keep V like this. But now I have a nice bound here, because remember, the number of vertices and the number of edges, I know these things. So I know that the number of edges is less than k, right? And I also know the number of vertices. It is k plus 1. So I can say that this is less than 2k over k plus 1, right? Because there's k plus 1 vertices in the graph, and there's less than k edges in the graph. So that means that only that will get bigger, right? Because this is exactly the same quantity here, but this is bigger than that. But now look at this. K over k plus 1, is that less than 1, equal to 1, or greater than 1? Which one is it? It's only one of them. One of these 3 that are possible here. Well, think of it. So imagine you had 1. 1 over 1 plus 1, that's 1/2. 2. 2 over 2 plus 3, it's 2/3, right? Can you see a way I could get that to be greater than 1 or equal to 1? No, because the quantities there, it's k, it's something over something that's slightly bigger than it. As a fraction, that's always going to be less than 1 in our case. So that is going to now just be whatever. So I could just say that's less than 1. So this has to be less, this whole expression is less than 2. Now this is where it gets fun. Now I have a bound on the average degree. So by the averaging principle, there exists a vertex W that has degree 0 or 1, right? Those are the only possibilities, right? Because the averaging principle tells you that there exists such a thing. That's the key way we're using it. So we're going to have 2 possibilities. W is going to have degree 0, and then we're going to consider the case when the degree is 1 for W. So the first case is when the degree of w is equal to 0. This is the easy case. It's so easy that I could just whip together a very trivial argument here. Since w has no adjacent vertices, well, remember, a vertex with a degree 0 is isolated, right? And there are other vertices in the graph, right? That's why I made sure that there was more vertices. So that means that this is disconnected. Since w has no adjacent vertices, and vertices, and there are more vertices than just w, G is disconnected. That's an easy case. G is disconnected in this case. So in this case, just to be clear, you have W just sitting out here. Then there's other vertices that might be doing all sorts of other stuff. But the point is that this guy is sitting out over here, can't be reached by anybody else. So now we're going to be using our induction step to our full potential here in the second case. So we're going to consider when the degree of W is equal to 1. So we're going to let X be the vertex adjacent to W. Now remember, in this setup, the way it works is that I'm going to have W, it has degree 1, so it's going to look something like this. And then there could be other stuff that's happening. So W is just sort of hanging off of X, okay, by this one edge. So we're going to let G prime be the graph where both W and the edge Wx, so the endpoints are W and X, are deleted. Now I want to remind you, this graph, the one I've just doodled over here, it has k plus 1 vertices, and it has less than what? How many edges? How many does it have? It has less than k, right? So when I delete this and delete this, notice that the number of edges and number of vertices goes down by 1. Interesting. Interesting. Then the number of vertices in G prime is k plus 1 minus 1, because we could deleted W, which equals k, and the number of edges in G prime is less than k minus 1. Because remember, originally it had less than k edges. Now, because I removed an edge, now it's less than k minus 1, right? so now you're staring at this and you're like, okay, what's going on here? Now this is where the fun of mathematical induction comes up. Okay, what did we say before? The graph, the new graph G prime, it has k vertices and less than k minus 1 edges. What do we know about that, presuming that we all previously proven it? We know we've assumed d of k holds, right? But what's d of k? It says that there is a graph with k vertices and less than k minus 1 edges. And that graph has to be disconnected, right? So that's the induction hypothesis. Let's use that. G prime is a graph with k vertices. And less than k minus 1 edges. So by the induction hypothesis, G prime is disconnected. So now we know G prime. When I took away these things, this has to be disconnected. So now we just have to reintroduce back in that edge and W. Vertex W is only adjacent to X in G. Therefore, G prime, and as a result, G remains disconnected when W and incident edge WX are introduced to G prime. Thus, this completes. Since now I've accounted for both cases, thus completes the induction step. Now that we have the base steps sorted out, we got the induction step, now we can apply the principle of mathematical induction and we're done. Therefore, by the principle of mathematical induction, D of n is true for all n greater or equal to 1. And that completes the proof. There we go. So now we know that if you have too few edges in your graph, the graph is going to be disconnected. Remember, the big idea that we had here was that we combined the handshaking lemma so we took the handshaking lemma, we used that to help us formulate a bound for the average degree of a vertex. Then we've seen that the average degree of a vertex, in this case, it can be too big. It can't be too big.